Hello chemistry students, I'm here to do lesson 9.5 with you, where we're going to take a look at gas stoichiometry and take another look at mixed stoichiometry calculations. So the goals for this lesson are, if you're given an amount of a gaseous reaction component, and that'll be expressed in liters when we're at STP, we want you to be able to perform the stoichiometric calculations to find the amount of another reaction component, and it could be a gas, and then you're also going to output it as liters of gas at STP conditions. And the second goal is just to be able to perform stoichiometry from really any input amount, moles, liters, grams, particles, and then ending at any of those varying amounts also. So let's get started, and we will take a look at a quick review of molar gas volume. Alright, so to review molar gas volume, as long as we are at standard temperature and pressure conditions, and that's 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure, as long as you maintain that temperature and that pressure, 1 mole of any gas will occupy 22.4 liters of space. So this is our equivalence from which we can do conversions from moles to liters of gas. 1 mole of any gas at STP conditions is going to be 22.4 liters of gas, and so that's where we build our conversion factors. Okay, on to an example problem.
So for this example on page 37, the human body consumes 1.03 times 10 to the negative 2 moles of O2 gas every minute. How much glucose is consumed each minute, and how many liters of CO2 is produced each minute? So we have a balanced chemical equation, correct?
Right, that's right here.
Alright.
It's already balanced, so this is glucose, C6H12O6, 6 oxygens. You get 6 CO2s and 6 waters.
And this is where the power of stoichiometry comes in. If you're given an amount of something, you can predict how much you actually are going to make, or theoretically should make. And then for the power of labs, it tells you how much you should make and then how much you made versus, the theoretical. So it's a good tool. So let's
probably
start.
The most often used tool in your arsenal, really. So we've got the starting amount, 1.03 times 10 to the minus 2 moles of oxygen. So since we're already at moles, we're already here, we're going to go straight to our mole ratio. Okay, and we can see that the ratio is 6 O2s to 1 glucose. So we're going to put 6 mole O2.
Do you want moles of glucose as the answer, or grams of glucose? It just says how much.
It does not say, does it? So I think we're okay. If it doesn't specify, we'd be fine to go with moles. So C6H12O6, the moles of oxygen will divide out. So you can see that we're just taking the given moles of oxygen and dividing it by 6. We need 1/6 as many moles of glucose as we have oxygen. So that is
1.72 3 sig figs times 10 to the negative 3 moles
times 10 to the minus 3 moles of C6H12O6. That is a 12.
If you say so.
So simple. Now the second one, this actually wasn't in the packet, but I tagged on this question to give us a little gas practice. So, if you respire that much glucose, the 1.7 times 10 to the minus 3 moles every minute, how many liters of carbon dioxide could you expect? And so we're going to go right back to the same starting point, that we have 1.03 times 10 to the minus 2 moles of O2. This time we're going to convert to liters. So the mole ratio works out a little bit differently in this one. It's 6 O2 to 6 CO2. So in other words, they're equimolar, 6 moles O2 to 6 moles CO2. So mathematically, this step is going to do nothing except change our unit for us from moles of oxygen 2 moles of carbon dioxide because the 6's divide out. 6 over 6 is 1. And then we are supposed to give the output in liters, so we need to remember, as long as we're at standard temperature and pressure,
we can just do as 22.4 liters is 1 mole.
1 mole of any gas, CO2 would be a gas, is just what Mr. Hunter said.
22.4 liters. And it turns out to be 0.231 liters of CO2.
So it's that simple. It's just combining things that we've already learned about, doing mole conversions to different ending quantities with that mole ratio that lets us swap back and forth between moles of one thing and moles of another one. All right, one more example and then we'll wrap up this lesson. Okay, chemistry students, so here's a second example problem, and this one, the output that we're asked for is mass, not liters of gas. So we have an equation, CaCO3 in the solid state is breaking down to form carbon dioxide gas and calcium oxide. It's a solid. So this is a decomposition reaction. You're going to need heat to make that reaction happen. And the question that we're being asked is, how many grams of the calcium carbonate are going to be needed to make that many liters of carbon dioxide gas? So it is a liters to mass conversion with some reaction stoichiometry. Alright, so we want to know how many grams of CaCO3 we need if we want to form that much carbon dioxide. Alright, so the first step, hopefully you've figured it out, but we need to go from liters of gas, so we want liters of CO2 here, to moles of CO2 there. So that's going to be 1 mole is 22.4 liters. So that cancels our liters of CO2. Second step, now we're going to go from moles of CO2 to moles of calcium carbonate. That's CaCO3. And when we look at our equation, we can see there's no coefficients, so they're assumed to be 1, so everything's a 1 in this. So for every 1 mole of carbon dioxide we get, we had to decompose 1 mole of calcium carbonate. So that changes our unit from moles of CO2 to moles of calcium carbonate. And of course our last step, we need to know how many grams is in a mole of calcium carbonate. And I looked it up, it is 100.09 grams of calcium carbonate in a mole. Okay, so there's our math. It's all set up for us. 3.45 divided by 22.4. The ones are going to cancel out, so we just take this divided by this and we multiply it by 100.09. So I'm going to pause it and work out the answer, and you do the same, and we'll see how we make out. Okay, so I've worked out the answer, and I am getting 15.4 grams of calcium carbonate. So if we decompose that much calcium carbonate, we should be able to produce 3.45 liters of carbon dioxide. Okay, so on the next slide, I'm going to hit you with a post-video question, and then you can try one of these on your own. And I think at this point, this is pretty much review and just maybe doing some additional work with the 22.4 liters to 1 mole. So hopefully you'll have an easy time of it. So here's your PVQ. We're going to use the same equation that we had in the last problem, and I've rewritten the equation here. So we're given a volume of gaseous product. If we have 11.6 liters of carbon dioxide formed, the question is how many particles, so how many molecules of the calcium carbonate, or I guess they would technically be formula units because it's ionic, but how many particles of this are going to be broken down to give us this much carbon dioxide. So give that one a try, see what you get.